Electrical engineering exam questions. Hello everyone, welcome to my channel. My name is Rafael. I am an electrical engineer, linguist and bilingual teacher of mathematics and physics from Brazil. And in this video, I'd like to invite you to observe the solution of 11 exercises on linear circuits applying Kirchhoff's current and voltage laws by means of nodal and mesh analysis. Let's go to the first exercise. Exercise number 1 says, for the circuit of the figure, find the voltage across the 10 ohms resistor and the current passing through it. Alright my friends, this is the exercise. Let's go to the solution. And to facilitate the solution of this exercise, we shall use some labels here. I'm going to call this current here I1. This I'm going to call I2. This will be I3 and this will be I4. And the value of the voltage at this node here, I'm going to call V, alright? After that, we are going to use Kirchhoff's current law, alright? To find the value of the voltage at the upper node, we are going to use Kirchhoff's current law. Alright, my friends? Observe that the sum of the currents that enter the node has to be equal to the sum of the currents that leave the node. Alright? And what is the current that is entering the node? It is 10 amps. And what are the currents that leave the node? I1, I2, I3, I4, and 5 amps. Okay? So we write it then. I1 plus I2 plus I3 plus I4 plus 5 amps. Okay, my friends? Now that we have understood the currents that enter and leave the node, we are going to use Ohm's law to write the currents in terms of this voltage and each of the resistances, okay? In this way, 10 amps is equal to V over 5 ohms plus V over 10 ohms plus V divided by 2 ohms plus V divided by 1 ohms plus 5 amps, okay? I am going to pass this 5 amps to this side. 10 minus 5 is 5 amps. And here to solve this part, we are going to use the lowest common denominator, alright? V times 1 over 5 plus 1 over 10 plus 1 over 2 plus 1. And if we solve, we find that it is V, the lowest common denominator here is 10. 10 divided by 5 is 2, plus 10 divided by 10 is 1, plus 10 divided by 2 is 5, plus 10 divided by 1 is 10. Okay, my friends? If we continue solving, we find that the V is equal to 2.78 volts. This is the value of the voltage at the upper node. But the exercise wanted us also to calculate the value of the current that passes through this 10 ohms resistor. Subsequently, we calculate the value of the current. I2 is equal to V divided by 10 ohms, okay? And the value of V is 2.78 volts. I2 is therefore 2.78 volts divided by 10 ohms, and this is equal to 0.278 amps. Okay, my friends? Thus, the voltage across the 10 ohms resistor is 2.78 volts and the current is 0.278 amps. Alright, my friends, this is all for exercise number 1. Let's go to the next. Exercise number 2. For the circuit of the figure, find the value of the voltage V2. Okay, my friends, this is the exercise. Let's go to the solution. And to determine the value of the voltage at node 2, we shall employ nodal analysis in conjunction with Kirchhoff's current law at both node 1 and node 2, okay? And for this purpose, we are going to use some labels here as well. We're going to call this current here I1. This current here, I'm going to call I2. This will be I3. This will be I4. And this will be I5. Alright, my friends. And remember that the sum of the currents that enter a node has to be equal to the sum of the currents that leave the node. For node 1, what is the current that is entering the node? It is I1. And what are the currents that leave the node? I2 and I3, alright? Consequently, I1 will be equal to I2 plus I3, okay? And how can we write these currents in terms of voltage drops and resistances? We're going to do as follows. I1 is equal to 100 volts minus V1 divided by 20 ohms. 100 volts minus V1 divided by 20 ohms. This is I1. And how about I2? I2 is equal to V1 divided by 20 ohms. And I3 now. I3 is V1 minus V2 divided by 10 ohms. Okay, then I write V1 minus V2 divided by 10 ohms. Okay? This is the equation, and if we simplify this equation, we find that I'm gonna store it here because I'm gonna need to erase this. So let's store it here. It is gonna be 4V1 minus 2V2 equal to 100 volts. Okay? Now we are going to do the same for node 2. Let me clear the board because I will need space here. The same analysis now for node 2. Node 2, okay? What is the current that enters node 2? It is I3. And what are the currents that leave node 2? I4 and I5. Then I write I3 is equal to I4 plus I5. How can we write I3 in terms of voltages and resistances? I3 is V1 minus V2 divided by 10 ohms, and I4 is V2 divided by 30 ohms. And how about I5? I5 is V2 divided by 10 plus 20, 30 ohms. Okay, so this is the equation for the currents entering and leaving node 2. Okay, and again, if we simplify this, we find that V1, I'm going to store it here, V1 is equal to 5/3 of V2, okay? I'm going to erase here because I'm going to need space here for more calculation. And applying this result here in the first equation, 4 times V1, but V1 is 5/3 of V2 minus 2 V2 equal to 100 volts. 4 times 5 is 20. 20/3 times V2 minus 2 V2 equal to 100 volts. If we continue solving, we ultimately find that V2 is equal to 21.43 volts and V1 equal to 35.71 volts. Okay, my friends, the exercise wanted only V2, and this is the solution of the exercise, and it is enough for exercise number 2. Let's go to the next. Exercise number 3. Find the voltage across the 10 ohms resistor in the circuit. The exercise wants us to calculate the voltage across this resistor, okay? And one of the several methodological approaches to solving this circuit involves its reinterpretation in terms of equivalent voltage sources through the application of Thevenin's and Norton's theorem. Alright, we are going to convert these two current sources into voltage sources. This is how we are going to solve this exercise. Obviously, there are other ways of solving this exercise. We chose this method. Alright, then I am going to convert firstly, let's do it. Let's convert this current source into a voltage source. This is 100 amps. This is 5 ohms. And I'm gonna label this voltage here Vx. And the current of the current source has to flow, and it's going to flow through the 5 ohms resistor, and when it flows it causes a voltage drop, and the value of the voltage drop is Vx equal to 5 ohms times 100 amps, and this is equal to 500 volts, okay? Likewise, we are going to do for this current source here. 200 amps. This is 20 ohms. And I'm gonna call this Vy, okay? Vy will be calculated in the same way. 200 amps times 20 ohms is equal to 4,000 volts. Alright, using this voltage source, this circuit becomes here 500 volts and here 5 ohms. Here 4,000 volts and here 20 ohms, okay? We are going to use this and this here to calculate the voltage drop across this 10 ohms resistor, okay? So let's do it. Let me raise it here to redraw the circuit. And the new circuit will thus be 500 volts, here 5 ohms, here 10 ohms, here 20 ohms, here 4,000 volts, and we are going to use a current here. I'm gonna call it I, and we can choose the direction of the current from left to right or from right to left. It doesn't matter, okay? You can do it. And in this way, this voltage here will be equal to this voltage here plus this voltage drop plus this voltage drop plus this voltage drop, okay? So 500 volts is equal to 5 ohms plus 10 ohms plus 20 ohms times I plus 4,000 volts. Of course, 4,000 volts is larger than 500 volts. We are going to find a negative value for the current, but we can't do this. The negative sign, of course, means that the current actually flows in the opposite direction. Okay, so I here is equal to 500 volts minus 4,000 volts divided by this number here is 35 ohms, and this is equal to negative 100 amps. And this negative sign doesn't mean that it is wrong. It simply means that the current is not flowing from left to right. Actually, it is flowing from right to left. Okay, my friends? Subsequently, we calculate the voltage drop. And to calculate the voltage drop, we simply multiply V, which is V1 minus V2. Okay? We are supposing here that V1 is higher in potential than V2, but actually it is not. Okay? It's equal to 10 ohms times negative 100 amps, and this is equal to negative 1000 volts. And what does it mean? Why this negative sign? We are supposing that the voltage drop is in this direction here. That's why the negative sign. But actually, V2 is higher in potential than V1. Then V2 minus V1 is positive 1000 volts. Okay? And this is the solution of exercise number 3. Let's go to the next. Exercise number 4. Determine the power delivered by each of the sources and absorbed by the resistor. Okay, my friends, this is the exercise. Let's go to the solution. And to solve this exercise, it is paramount that we observe that the current of the current source must flow somewhere. And it turns out that it is going to flow through the resistor. Okay, the current of the current source is going to flow through the resistor, and it is going to cause a voltage drop here, and the value of the voltage drop is V equal to 5 ohms times 2 amps, and this is equal to 10 volts, and this 10 volts precisely matches the voltage of the voltage source. Okay? Then this V here will appear here, and the V is precisely equal to this, which means that there is no current here. This current here is 0 amps. What does it mean? It means that the voltage source is not contributing with current. Okay, it is not contributing with power. The power is being drawn from this current source. Okay, my friends? Subsequently, we calculate the powers, and the power delivered by the voltage source is 10 volts times 0 amps, which is equal to 0 watts. And how about the power delivered by the current source? It is going to be 2 amps times 10 volts, because on top of the current source there is this voltage here of 10 volts. Okay, so 2 times 10 is 20 watts. And finally, we're going to calculate the power absorbed by the resistor. It is equal to 5 ohms times 2 amps squared, and this is equal to 20 ohms. Okay? What does it mean? It means that the voltage source is not contributing with power. The power that the resistor is absorbing is being delivered only by the current source. Okay, my friends, and this is all for exercise number 4. Let's go to the next. Let's go to exercise number 5. Exercise number 5. Simplify the network between terminals A and B. into a circuit with only one source and only one resistance. Okay, my friends, this is exercise number 5. Let's go to the solution. To solve this circuit, we shall convert voltage sources into current sources and vice versa, in accordance with Thevenin's and Norton's theorem. Okay, my friends, firstly, we are going to convert this voltage source into a current source. It is going to be what is the value of I1? The value of I1 is simply the division between 4 volts and 2 ohms, and this is equal to 2 amps, okay? Thus, this circuit can be remodeled as a current source of 2 amps with the resistance two ohms, okay? We're going to use it. Next, we converted this into this voltage source into a current source as well. It is going to be okay, and the value of I2 is equal to 3 volts over 1 ohm, and this is equal to 3 amps. Thus, this can be remodeled as a current source with a resistor likewise. We are going to do for this voltage source. The voltage source will be here, 6 volts, 3 ohms, and here the output terminals short-circuited. Observe that here it is different. I made a mistake here. Observe that the polarity is inverse. Then it is in this way, and the current flows upwards. Okay? And I3 will be equal to 6 volts divided by 3 ohms, and this is equal to 2 amps. And the circuit thus becomes a current source but pointing downwards, 2 amps, and here the resistor. Okay? We are going to use this, and this here to simplify the circuit, okay? let me erase the board and I'm gonna show you how the new circuit is gonna become. Thus, the circuit may be redrawn after these changes are implemented as follows. There will be here 1 amp, and here 2 amps, two ohms, here 2 amps, three amps, 3 ohms, 1 ohm. This is terminal B and this is terminal A. Okay? Subsequently, we combine the resistances and the current sources. Observe that these current sources are additive. They inject current at the same terminals. Okay, so current source equivalent number 1 is equal to 3 amps. And observe that these current sources are subtractive because they inject terminals at different, they inject current at different terminals. Okay, so the equivalent current source number 2 is equal to 1 amp. And how about the resistances? This and this. This equivalent resistance will be the parallel combination of these two resistances. Observe that they are in parallel. It is 2 ohms in parallel with 2 ohms, and this is equal to 2 times 2 divided by 2 plus 2, which is equal to 1 ohm. Likewise, we do for this. Observe that they are in parallel, and resistances in parallel are calculated like this, which is equal to 3 ohms in parallel with 1 ohm, and this is equal to 3 times 1 divided by 3 plus 1, and this is equal to 3/4 of the ohm. Okay? Then the circuit will be this 3 amps, one ohm, one amp, 3/4. This is terminal A, this is terminal B, okay? The next step consists of converting the current sources into voltage sources. We're going to convert the current sources into voltage sources now. This exercise is laborious, but quite straightforward if we go slowly. Let's take this current source here. Three amps. And here 1 ohm. I'm going to label the output terminals, the voltage at the output terminals VA, and VA is equal to 3 amps times 1 ohm, and this is equal to 3 volts. Likewise, we are going to do for this. One amp three-fourths of the ohm. I'm gonna label this VB, and VB is equal to 1 amp times 3/4, and this is equal to 3/4 volt. Okay? In this way, we can modify this into this. Okay, terminal A will be here, and here 3 volts. This is 1 ohm, this is terminal A. Here 3/4 ohm, and here terminal B. Okay, observe that these are additive, okay, and the resistances are in series. Then the equivalent resistance is 1 plus 3/4, and this is equal to 7/4 ohms, and the equivalent voltage is equal to 3/4 plus 3, and this is equal to 15/4 volts. Okay, then the circuit, the final circuit is this, plus minus V equivalent, which is equal to 15/4 volts, and this is R equivalent, which is equal to 7/4 ohms. Okay, so this is the reduced circuit. Okay, this is the final circuit. All right, and this is the answer of exercise 5. Let's go to the next. Let's go to exercise number 6. Let's go to exercise number 6. For the circuit of the figure, calculate the power dissipated in the 3 ohms resistor. Okay, my friends, this is the 3 ohms resistor, and the exercise wants us to calculate the power dissipated in this resistor. Observe that we are dealing with a super mesh here. Okay, there is a super mesh here. Alright, can you see that? If a current source is common to two meshes, we can create a super mesh by avoiding the current source and any passive element connected in series with it. Alright, my friends, so this is how we deal with a super mesh. And to calculate what the exercise wants us to calculate, let's use some labels. I'm gonna call the current here I1. I'm gonna call the current here I2. And I'm gonna call the current here I3, okay? And applying KCL to mesh 2, this here, we obtain that, firstly, let's consider this 1 ohm resistor. Observe that while I2 goes upward here, I1 goes downward, then it is going to be 1 ohm multiplying I2 minus I1. Now let's consider this 2 ohms resistor. The voltage drop is written as 2 ohms times I2 plus, let's consider now this 3 ohms resistor. While I2 passes going this direction, I3 goes that direction. Then it is going to be 3 ohms multiplying I2 minus I3, and this has to be equal to 0. If we simplify this expression, we find that I1 minus 6I2 plus 3I3 is equal to 0. Okay? This is what we get when we analyze this mesh here. Now let's consider the combined mesh equations for mesh 1 and 3, neglecting the super mesh composed of the 7 amps current source and this 1 ohm resistor. Okay, if we inspect, let's begin with this voltage source. 7 volts is equal to let's see this resistor here. I1 goes downward and I2 goes upward, then it is 1 ohm. I1 minus I2. Let's see now this, okay, because we are avoiding, when we have a super mesh, we can simply neglect this. We can neglect this, okay, and we are going to consider the circuit as if the current is flowing here and here, okay, here and here. We are going to avoid this altogether, okay. Then it is 3 ohms current I3 goes this direction and I2 this direction, I3 minus I2, and through this 1 ohm resistor passes I3 plus 1 ohm times I3, okay? And if we simplify, we find that it is equal to, I'm going to store it here, 7 volts is equal to I1 minus 4I2 plus 4I3, okay? So these are the equations that we are working with, okay? Store it there. Now looking at the super mesh, we see that, let's look at the super mesh, we see that I1 passes downward and I3 upwards, then I1 minus I3 is equal to 7 amps, okay? And in this way, we understand that I1 is equal to 7 amps plus I3, okay? And we are going to apply this here in the first two equations. Here, we are going to apply this here and here, okay? And if we do this, we're going to find that it is equal to 7 amps is equal to 7 amps plus 4I3 minus 6 I2 equal to 0, and 4I2 is equal to 5I3, okay? And now we have two equations with two variables. It is easy to calculate. We can simply substitute. We can calculate by substitution, and ultimately we find that I1 is equal to 9 amps, I2 is equal to 2.5 amps, and I3 is equal to 2 amps, okay, my friends? And now we can calculate the power. The exercise wanted us to calculate the power dissipated in this component here, and we can calculate the power by doing this. It is 3 ohms times, here I have, see that I2 is greater than I3, so it is gonna be I2 minus I3 squared. P is equal to then 3 ohms times 0.5 amps squared, and this is equal to 0.75 watts. Alright, my friends, and this is precisely the solution of the exercise. This is the power dissipated in this 3 ohm resistor. Okay, my friends, and this is all for exercise number 6. Let's go next. Let's go to exercise number 7. Exercise number 7, for the circuit of the figure, determine the voltages V1 and the V2. Okay, my friends, this is the exercise. Let's go to the solution. Observe that we've got a super node in the middle of the circle. There is a super node here. Okay? Since the current through the voltage source cannot be modeled, it is impossible to write nodal equations for nodes 1 and 2 independently. Therefore, we are going to create a supernode here because we cannot write node equations for node 1 and node 2 independently, because we cannot model the current flowing here, okay? There is no resistance. As we cannot do this, we are going to use a supernode, okay? Let's label this current here I1. Let's label this current here I2. Let's label this current here I3. Let's label this current here I4. And let's label this current here I5. Okay? Looking at the supernode, we see that currents I1 and I5 enter the node. And the currents I2 and I4 leave the node. We are going to neglect I3, okay? We are going to use a supernode here and neglect I3. We are only seeing what enters here and what leaves here and here, okay? So I1 plus I5 is equal to I2 plus I4, okay? I1 is 4 amps and I5 is 9 amps. 4 amps plus 9 amps is equal to I2. I2 is V1. Observe that I2 is V1 divided by a half. V1 divided by a half. And I4 is V2 divided by a sixth. If we solve, we find that 13 amps is equal to 2V1 plus 6V2. Inside the supernode, we see that V1 minus V2 is equal to 5 volts. Applying this to the first equation, we obtain that, okay, if V1 is equal to 5 volts plus V2, applying it there, we obtain that it is 13 amps equal to 2, 5 volts plus V2, plus 6V2. And we have here one equation with only one variable. It is solvable. We can solve it for V2, and V2 is equal to 0.375 volts, and V1 is equal to 5.375 volts. Okay, my friends? And this is the solution of the exercise. Let me remember the exercise when it has to calculate the voltages at nodes V1 and V2. And this is the answer, okay? This is the solution of the exercise. We used a supernode here because we understood that we could not model the current that flows here. okay, because there is no resistance, then we used a supernode. We considered all this as a node and observe the currents that enter through here and leave through here, and we calculated this. Okay, my friends, this was exercise number 7, and let's go next. Let's go to exercise number 8. Exercise number 8, determine the current I in the circuit. Okay, this is a simple exercise. The exercise only wants us to calculate the value of this current. And to do so, let's use some labels here. I'm gonna label this current here I1, this current here I2, and this current here, and this voltage here, the voltage of this node here, I'm gonna call it Vx. Okay, my friends? Observe that while current I1 and I2 enter the node, current I leaves the node, alright? Consequently, I is equal to I1 plus I2, okay? And we already know that I1 is 4 amps, okay? So I is equal to 4 amps plus, and how can we write I2? I2 can be written as it is flowing this way, it is 20 volts minus Vx divided by 2 ohms. Alright, my friends? We can also work on this, because here there is I and we don't know I, and there is Vx here. We have 2 variables. Let's write I in terms of this voltage and this resistance. It is going to be Vx divided by 2 ohms. Now we have only one variable. We have Vx here and Vx here, okay? We are going to work on this equation here. Let's pass this to this side. It is Vx over 2 ohms. Passing this negative to the other side, it becomes positive, plus Vx divided by 2 ohms, and this is equal to 4 amps plus 20 volts divided by 2 ohms is equal to 10 amps, okay? Vx over 2 plus Vx over 2 is equal to Vx. Vx, but we have this ohm here passing to the other side, it becomes voltage, okay? Ohms times amps is voltage, alright? Then we solve and find that it is 14 volts. Okay, you have to work with this as well, not only with the number. We have to work with this, the ohm and the amp. Ohm times amp is equal to voltage. Finally, we can calculate the value of I. The value of I is simply Vx 14 volts divided by 2 ohms, and this is precisely 7 amps, okay? And this is all the exercise wanted from us. The exercise wanted us to calculate the value of the current and the value of the current is 7 amps. Okay, my friends, this is all for exercise number 8. Let's go to the next. Let's go to exercise number 9. Exercise number 9. Calculate the voltage Vx and the current Ix in the circuit. Okay? This is the exercise, and this is what we are going to do. We are going to calculate the voltage Vx and the current Ix. Alright? Let me use some labels here again. I'm gonna call this current I1. This current here I'm gonna call I2, and the other current is Ix, my friends. And applying the nodal rule at the Vx, we can find the value of the voltage at the node. Observe that the sum of the currents that enter the node has to be equal to the sum of the currents that leave the node. And the current entering the node is I1. And what are the currents that leave the node? The currents that leave the node are I2 and Ix. Okay? These are the currents. And the current I1 we already know. And the value of I1 is simply the value of this current source, and it is equal to 10 amps, okay? And how about I2? I2 is Vx divided by 4 ohms. Subsequently, we calculate Ix, and Ix will be written in terms of the voltage source and the voltage at the node. Observe that it is additive, okay? This voltage here is additive to this voltage here. Then plus Vx plus 4 volts divided by 2 ohms. We can do this. 10 amps is equal to Vx over 4 ohms plus Vx over 2 ohms plus 4 divided by 2 is 2 amps, okay? From which we get that Vx is equal to 10.66 volts. Simply, we've solved one of the questions. One of the questions was calculate the value of the voltage Vx. Now we can calculate the value of the current Ix, and the value of the current Ix can be calculated using this. Ix is equal to 10.66 volts plus 4 volts divided by 2 ohms. Okay? This is the current Ix. And ultimately, we find that Ix is equal to 7.33 amps. Okay? And this is everything. All that the exercise want us to calculate. Thus the value of X is 10.66 volts, and the value of Ix is 7.33 amps. Okay, my friends, and this is all for exercise number 9. Let's go to exercise number 10. Exercise number 10, determine the voltage V2 in the following circuit. Alright, my friends, this is the exercise. Let's go to the solution. The exercise wants us to calculate the value of V2, okay? And to begin solving this problem, we may combine the 220 ohms resistances connected to node 2, okay? We are going to combine these resistances here, and the equivalent resistance is equal to 20 times 20 divided by 20 plus 20, and this is equal to 10 ohms, okay? They are connected in parallel, and when combining resistances in parallel, we use this rule of thumb here, the product over the sum, okay, my friends? And then the circuit can be redrawn as this. We can simply erase this and this and connect this 10 ohms resistance here, alright? And let's use some labels here. I'm gonna label this current here I1, I'm gonna label this current here I2, and I'm gonna label this current here I3. Okay? The sum of the currents that enter the node has to be equal to the sum of the currents that leave the node. Alright? And what is the current that is entering the node? It is I1. I1 enters the node. And what are the currents that leave the node? They are I2 and I3. Okay? How can we calculate I1? I1 is 60 volts minus V2 divided by 10 ohms, okay? 60 volts minus V2 divided by 10 ohms. And how about I2? I2 is simply V2 divided by 10 ohms, okay? And I3, observe that this voltage here, 5 volts, appears here as well, okay? Okay, appears here as well. Then I3 will be equal to V2 minus 5 volts divided by 10 ohms, okay? Now it's simple mathematics. It's simple mathematics because we have only one variable here. Okay, we have only V2 here. We have only one variable, and whenever we have one equation and only one variable, we can simply calculate. And it is easy. I invite you to try in your house. And after solving this, we find that V2 is equal to 21.6 volts. Okay, my friends? And this is the solution of exercise number 10. Alright, my friends. Let's go to the last exercise. Alright, my friends, let's go to the last exercise. Let's go to exercise 11. Find the current through the 100 ohms resistance in the circuit. Okay, my friends, this is the exercise. And the exercise wants us to find the current through this resistor here. And to do so, we are going to use some labels. I'm going to call this current here I1. I'm going to call this current here I2. And I'm going to call this current here I3. Okay, my friends? And this voltage here, I'm gonna call Vx. And applying the node rule and node X, we find that we have to remember that the sum of the currents that enter a node has to be equal to the sum of the currents that leave the node. Alright? And what is the current that is entering the node? It is I2. And what are the currents that leave the node? They are I1 and I3. Okay, my friends? Simple. And what is the value of I2? I2 is this current here, 10 over 4 amps. And how about I1? I1 is 50 over 4 amps. And how about I3? I3 is simply Vx divided by 100 ohms. I am going to pass this side, and it is 10 over 4 amps minus 50 over 4 amps, and this is equal to Vx over 100 ohms. Simple mathematics, isn't it? Simple mathematics. If we solve this, we find that Vx is equal to negative 8,000 volts. Okay, this is the value of Vx, 8,000 volts. And finally, we can find the value of I3 by simply dividing this by this. Then I3 is equal to Vx divided by 800 ohms, and this is equal to negative 8,000 volts divided by 100 ohms, and this is equal to negative 10 ohms. Okay, my friends? And what does it mean? There is a negative sign there. What does it mean? It means that actually the current is flowing in the opposite direction. Okay, it is not wrong. If you are calculating in your house or in your office and you find a negative sign here, it is not wrong. Okay, it means simply that the current is flowing in the opposite direction. All right, my friends? And this is all for exercise number 1, and this is all for this video, my friends. I hope you learned from the video and enjoyed the video. My name is Rafael. As I said, I am a teacher. If you want to book a lesson with me, use my WhatsApp number. Goodbye.